for coming. So my today's talk is, like as mentioned just now, is the machine learning and dynamical systems, a meeting in reproducing Kernel Hilbert spaces. So the goal of this talk is to show that the two fields of machine learning and dynamical systems meet in a mathematical structure called producing Kernel Hilbert spaces. So there is unifying framework for this interface. So this is like work I have been doing for a long time now, about probably yeah, almost 15 years. So there have a lot of people here, a lot of collaborators, and yeah. So that's yeah. So the general idea is to the general question is how to analyze complex systems. So there are many approaches to analyze complex systems, and among the current ones, is the theory of dynamical systems. That is a classical one. That has been developed by Poincaré and Lyapunov in the late 1800s. And then it allows to analyze complex systems when the model is known. So it also offers non-trivial ways to analyze dynamical systems. It has the status of theory, but it is currently limited to low-dimensional models and some few infinite-dimensional systems. So on the other side, we have machine learning that is quite popular. So it is concerned with algorithms designed to accomplish a certain task whose performance improves with the input of more data. So it allows the analysis of some very high-dimensional complex systems on the basis of data when the model is not even known. But it is currently limited to due to the fact that the techniques that are used are mostly techniques and algorithms. There is no methodologies. The theory is still underdeveloped, and it's not clear why the algorithms work and what is their domain of applicability. So it's like here it makes sense. By looking at these two definitions, it makes sense to combine between dynamical systems and machine learning to strengthen each other. And this combination goes in the following directions. So the first direction is machine learning for dynamical systems, where the goal is to analyze dynamical systems on the basis of observed data rather than attempt to study them analytically. So this would allow to extend the boundaries of the classical theory of dynamical systems. And then you have the other side, which is like dynamical systems for machine learning, where the goal is to analyze algorithmic machine learning using tools from the theory of dynamical systems. So here one would look at algorithmic machine learning as dynamical systems where time on the computer, not time in a clock or in a watch, like in the classical theory of dynamical systems. And so this would allow to give solid foundations to the existing methods and understand their true potential and limits, and eventually identify the domain of applicability of the algorithm of machine learning. So as pointed out by Steve Smale in about around 2007, so he mentioned that the interaction between dynamical systems and learning theory is an important problem. So he mentioned that the unification of dynamical systems and learning theory is a major problem, and that another problem is to develop a comparative study of useful algorithms using the theory of dynamical systems. And so speaking of Steve Smale, this is how I got involved in the field. So he is the one who encouraged both me and Jake Bouvry. So both of us were at Duke University in this period of 2007-2010. And so this is how we end up being involved in the field. And that's what we wrote about 10 years ago, where we said that it's easier to simulate a dynamical system and analyze the empirical data rather than attempt to study them analytically. And at that time, the mathematical theory necessary to analyze dynamical systems on the basis of observed data was still largely underdeveloped. So our approach is to use a special kind of Hilbert spaces that are called reproducing Kernel Hilbert spaces to develop the database qualitative theory of dynamics for analysis, prediction, and control. And so here the Hilbert space will be constructed from data. So we have data, and then we construct Hilbert space where the analysis becomes simpler. So we are going to view reproducing Kernel Hilbert spaces as linearizing spaces, but here linearizing spaces is something to be understood in a loose way. So by linearization, we say, we mean that nonlinear systems will be embedded into reproducing Kernel Hilbert spaces where linear system theory will be applied. And the main motivation, but it's not only the only motivation, but the main motivation is that working in reproducing Kernel Hilbert spaces allows to find a nonlinear version of algorithms that can be expressed in terms of inner products. So in spirit, I mean, this seems to be like similar to what people did like in quantum mechanics. And I think there is like some flavor there. I mean, like quantum mechanics, so you have data and then you have observables, and then one constructs a Hilbert space where computations become simpler. And I think around that time, like in the 30s, people had complex problems, but they did not have the computational power. So the goal was to try to find ideas to make problems simpler by constructing spaces where computation becomes simpler. And yeah, so that's the flavor that is there. I mean, the outline of the talk is as follows. I mean, I'll talk about a little bit about RKHS, function approximation, and probability measures in reproducing Kernel spaces. I'll talk about kernel flows and then how to choose the kernel in reproducing Kernel Hilbert spaces. I'll talk about like parametric, non-parametric kernel flows, irregular time series, partial observations, and sparse kernel flows. So I'll talk about also detection of critical transitions for some slow-fast SDEs. And yeah, so I also, if I have time, I'll talk about central manifolds. I'll talk about database version of the central manifold theorem, and also on the construction of Lyapunov functions in reproducing Kernel Hilbert space, if I have time. So I'll probably not have time to cover the other parts, but yeah, so I'll just talk and then until you tell me. Yeah, please tell me when I have only 5 minutes left. Yeah. And yeah, so the summary of the approach is that we assume that there is a phi, there's an embedding that goes from Rn into H, where H is an RKHS, where we perform an analysis that is not necessarily a linear analysis in H and then come back to Rn. The transformation phi is obtained from the kernel that defines the RKHS. So here we are at the RKHS, and the kernel is a function of two variables. So K, so to go from the ambient space Rn into H, I mean, one uses the second variable x, y as the x of Ti. So as I said here, we are using data to construct like measurements or data to construct a Hilbert space where computations become simpler. Now, as I said, I mean, this has a similar spirit as quantum mechanics. So the historical context is that it's this Hilbert space that appeared in the 30s as an answer to the question, one, is it possible to embed the metric space into Hilbert space? So the metric space in a way are like nonlinear spaces, and Hilbert space is a linear space. And the idea was to map or to transform computation and make them simpler by working into simpler mathematical structure that is the Hilbert space. And the answer was that if the matrix satisfies certain conditions, it is possible to embed a metric space into a special kind of Hilbert spaces that are called reproducing Kernel Hilbert spaces. And so this is how they come from. And then their properties have been further studied in the 50s and later on by Aaron Jan Schwartz. And then they died a little bit, and then they were resurrected later on in the 90s by Wahba, and then later on in the 2000s by Smail and his group. So what are they? I mean, before anything else, they are Hilbert spaces. So with extra properties, the first property is the producing property, that is the one here in the I, property I, that the evaluation functional can be written as an inner product. So we have f of x equal to the inner product of f with k. And then the second property is that the closure of the span of k is the space itself. So in other words, an RKHS is Hilbert space with the reproducing kernel whose span is dense in H. So there are like few properties, I mean, that are important. That the RKHS is unique. So given a kernel, we have a unique RKHS that is associated to it. The feature map is not unique. So we can have like many feature maps for the same RKHS, but the kernel is unique. So we have positive definiteness according to this definition, and we have also this property that we can decompose kxy as we can write it as the inner product of kx dot with ky dot in H. And this gives us that is what the so-called canonical feature map, also called the Aron-Jones feature map, that is at phi cx is equal to kx dot. So you see here kxy will write as phi cx with phi cy in H. Mercer kernel is a kernel with the extra property that it is continuous, and the fact that Mercer kernels are positive, definite, and symmetric reminds us of similar properties of Gramians at covariance matrices, and this is exactly what these are the kind of properties that we'll be using in this work. So examples is the monomial, the Gaussian hyperbolic tangent kernels, yeah. So another way of finding the feature map, as I said, there are like feature maps are not unique. So one of them is to use the canonical feature map, that is the one here. And that this is what we used in our work. The other one is to use Mercer theorem, where one associates an integral operator to the kernel, and then from there computes the eigenvalues and the eigenfunctions, and then we'll get this decomposition that we get that kxx prime is the sum of lambda j of cjx cjx prime, and since k is positive, then the eigenvalues will be positive, and so we get the so-called Mercer feature map, that is the square root of the eigenvalues of the integral operator times the eigenfunctions. So this is what we call the Mercer kernel feature map. Yeah, as I mentioned earlier, even here, the phi is not unique, but even here, phi is not unique because it depends on the measure that appears in the integral operator. And in general, it's also phi is difficult to compute because it's not that easy to compute eigenfunctions and eigenvalues of an integral operator in general. So here I was just showing that how to compute feature maps without using Mercer feature map. So here, for example, this is like an example of non-Mercer feature map. So for example, we start with the polynomial kernel. So kxt is equal to the inner product. Let's start with R2, for example. So inner product of x with t to the power 2. So we get like x1 t1 plus x2 t2 to the power 2. So you can square it. So it becomes like x1 t1 square plus 2x1 t1 x2 t2 plus x2 t2 square. And then this you can be written as x1 square x2 square square root of 2x1 x2 times t1 square t2 square square root of 2 t1 t2. So you see by so the embedding the phi here goes from R2 into R3 and then takes maps x1 x2 into this mapping x1 square x2 square square root of 2 x1 x2, and this is like a direct way of computing the feature map. So one can do the same thing for a Gaussian kernel, and we'll go from R2, for example, to L2, little L2. So even though I said it's not necessary to use Mercer theorem, but at least it's useful in finding error estimates and study the smoothing properties of kernel. So one of the applications of kernel methods is in function approximation, where one is interested in approximating an unknown function from random samples. So we have an unknown function f that goes from x to y. We have random samples x, I, y, I varying from 1 to n. And so here what we are going to do, the way it's done, that you assume that there is a random probability measure that governs the random samples. Then we assume that we want to minimize this error, and then the integral of fx minus y squared d rho. And then the function that minimizes the error, in principle, is given by the following expression. So f rho x is given by the following integral. But since we don't know rho, then it's hard to find this approximation. So what happens in practice is that one discretizes the previous integral. Then we have f is equal to 1 over m sum of fxi minus yi square plus lambda norm of f square h. And so lambda is the regularization parameter. And yeah, so once we discretize and regularize the problem, so this problem admits a solution. So the approximation, the approximant of the unknown function is fs x is equal to sum of cj kx xj. And then if you remember well, that the KXXJ is the canonical feature map by Aronjan, which is the sum of CJ, PJX. And the CJs themselves, they do satisfy a system of linear equations that is given by the following system of equations of lambda MCI, the sum of KXI, XJ, CJ is equal to YI, so, which is consistent with what we mentioned earlier, that reproducing Kernel Hilbert spaces, they have this property of being linearizing spaces. And in this context, I mean, we call learning the process of approximating the unknown function f from the random samples on Z in the RKHS K, HK, where K is the kernel associated to A. Another application is the problem of change point detection. So we'll consider a sequence of samples x1 to xn in some domain capital X. So we are interested in detecting a possible change point tau, such that before tau, the samples xi follow probability distribution p. And then after tau, we are following the data are following probability distribution q. And then we want to find tau. So the approach here is to map the data into some RKHS and then compute a measure of discrepancy delta n that is small if p is equal to q and large if p and q are far apart. So here, because we are going to, as I mentioned, we want to argue for RKHS as linearizing spaces. So the measure of discrepancy that we'll be using is the maximum discrepancy, which is given by the following object here, which in practice, what it means that we are mapping the probability distribution P in capital P into some into some Hilbert space RKHS H, and then compute the mean in the RKHS, and this is what we call the kernel mean embedding. So the kernel mean embedding is the mean of the probability distribution after being mapped into the RKHS. And the maximum mean discrepancy between two probability measures is the difference between the means. So you see, when we are using a linear quantity, that is the mean. And then we are looking at we are defining the MMD as being a metric between probability measures. That is the difference between the means of the probability measures after being mapped into the RKHS. So this, so here we don't need actually to do the computations in H, but we can compute them directly from the kernel. So the MMD PQ between two probability measures P and Q can be directly computed using this formula here, using the kernel. So we have like X are from capital from P, and then Y are from Q, and then one computes just the kernel, the kernel. Which is in a way like a measure of similarity between the variables. So this expression here, I mean, that we see here is not a metric, technically speaking. It is a pseudo metric on distributions. That is, it satisfies all the qualities of a metric except that the MMD is equal to 0 if and only if P is equal to Q. But for the MMD to be a metric, it is sufficient that the kernel is characteristic. That is, that the map mu P from P to H is injective. And this is usually satisfied by the Gaussian kernel, both on compact domains and on RD, for example. This is just like an illustration of what we are doing here. We take, for example, a probability measure P. So we map it into the RKHS, probability measure Q, map it into the RKHS, and then we compute the means, and then this is what the MMD is about. And here, for example, you see the probability distribution is P is blue, red, and then by computing the MMD, you see it's maximal when the two are far apart. So we have also this property here that for characteristic kernel, the MMD meteorizes the weak star topology on probability measure. That is that the MMD between Pn and P tends to 0 if and only if Pn converges to P. So what this means that we have convergence in distribution if and only if we have convergence in the MMD. And it is an integral probability metric that can be computed directly from the data without having to estimate the density as an intermediate step. So this is the advantage of the MMD, and compared to other metrics, where, for example, the Kullback-Leibler divergence, where one needs to know what the probability distributions are, I mean, their expression before computing the metric. So, and then if one uses data, then one has to estimate the probability distribution from data, then use the formula for the KL divergence. So here we don't need that. We just compute the MMD directly from data. So, for example, this expression that the n-bias estimate of the MMD is the following. So that is that the MMD, square is the sum of kxixj plus kyiyj minus kxiyj minus kxjyi. And that's exactly the expression we'll be using for our computations. So now the natural question is, remember, we said that the main motivation here is to, given data, we construct a Hilbert space from the data where the computations become simpler. And so the natural question is how to choose the kernel. So this is the common question. So here we'll be using the method of kernel flows that one of my colleagues, Human Ohadi, developed a few years ago. So here we come back to the same problem of given some input-output data, x1, y1 to x and yn. So we have like endpoints, and we are interested in approximately unknown function from random samples. So this problem, as we know, is ill-posed. But in the setting of optimal recovery, this problem can be turned into a well-posed problem by restricting candidates for you to belong to a certain Banach space with the following norm. And the problem of approximating the unknown function is the problem of an optimal recovery problem, where we are interested in minimizing the following relative error. So like mean, it's like a mean max problem. So mean with respect to V, max with respect to U of this relative error. So U is the true function, and then V is the approximant. And the method of kernel flows is based on the premise that a kernel is good if there is no significant loss in accuracy in the prediction error, if the number of data points is halved. So this is what it means in practice. So that we'll have this relative error rho, and V star is the approximant evaluated at capital N points, and Vs is the approximant with capital N over 2 points. So we are interested in minimizing this error that is between V star and Vs, and then we normalize just to make sure that the rho is between 0 and 1. And so this is like the expression of the approximant with capital N over 2 points. And so what happens in practice that this is we are going to end up having a trainable machine learning method that is not a neural network. So here we given capital N points, we take we're given like a large number of points, we extract capital N points, and then from there, this is like the first sample, and then we take a subsample with capital N over 2 points, and then we compute the relative error as being 1 minus y transpose, so k theta xc minus 1 yc, with yc is corresponds to capital N over 2 points. And then one yf is that which corresponds to capital N points. And then we evolve theta in the gradient descent direction of rho. So that is, we are going to write down as theta k plus 1 is equal to theta k minus delta gradient of rho with respect to theta, and then repeat. So here our goal is to forecast, and we are going to apply this method to learning chaotic dynamical systems. So given time series x1 to xn, for example, we want to forecast xn plus 1 given this knowledge. And then we are going to work under the assumption that this time series can be approximated by a solution of a dynamical system of this form. And given the approximation of given tau, here we are going to assume that the tau, which is like the time delay that is required for the approximation, we assume that it is known. But yeah, if you want to estimate it, then we have developed a method about how to estimate the tau dagger in the paper. So you just have to look at the paper to find tau dagger. So introduce this concept of energy for time delays. And so here we are going to view this problem as a problem of interpolation. Like in the same way, like we want to we want to recast this problem of approximating an unknown function from random sample as a problem of approximation of a dynamical system, which is like approximating the F dagger. So here the X will play the role of this like path of xk to xk plus 2 minus 1, and yk is the next iteration. So which will be yk is equal to xk plus 2, and then capital N is that's the number of iterations that we need. Yeah, so given what I mentioned before about like approximating an unknown function from the random samples, we know that this problem can be approximated as with F dagger. So k capital k little x capital X k x x minus 1 y, and then we are going to add the regularization term here. And so here we extended also we entered, so we reformulated the problem of Kernel flows by introducing like new variants, because we are looking at the problem of learning a dynamical system. So it's not only about learning an unknown function from random samples, but we are also looking at the problem of dynamical systems behavior. So we are not only interested in the short term, but we are also interested in the long term behavior. So we want to also introduce, we want to also learn a kernel that takes into account our objective. So the objective is not necessarily just approximating F and viewing it as a function, but we are also interested in something else. So here, so this is the first one that we use, but we also look at Lyapunov of exponents. So if in the case of chaotic dynamical system, so we want to say that the kernel is good if the estimate of the maximal Lyapunov exponent obtained from the kernel approximation of the dynamics does not change much if half of the data is used. So we introduce this this metric, but you can also use other metrics. And also add other Lyapunov exponents here. If you are not interested only in the maximum Lyapunov exponent, you can use like another other Lyapunov exponents, especially if you are dealing with the hyper chaotic dynamical system. And then we can also use another metric if you are looking, for example, at the statistical properties, where we are going to say that kernel is good if the MMD between two samples of the time series, or one sample and then a subsample of this sample is small. So the raw MMD is the MMD between S1 and S2. Now, I forgot actually to talk about the fourth metric that we used recently, which is about about attractor reconstruction. So where we are going to say that the kernel is good. So this will be like a fourth metric here. The kernel is good if the Hausdorff distance between the reconstruction of the attractor from capital N points versus a reconstruction of the attractor from capital N over 2 points is small. So that would be like the fourth metric. So we looked at some prototypical models, and we used the following kernel as a start. For example, we start with a Bernoulli map, so xk plus 1 is equal to xk mod 1. So we say that we see that there is like an improvement. So the second figure is without learning the kernel. First figure is with learning the kernel. So we see an improvement. So blue is true and red is approximation. So here, then this is like for one initial condition. The right figure is for different initial conditions. So green is without training, and then blue is true, and red is approximation. We also look at Lorentz, the Lorentz system, and so these are the time series generated by the true and the approximation of the system. So blue, so like X, Y, Z, and these are the errors. So we see, so here like before training, after training is red, before training is green. So this is for the X component, Y component, and Z component. Now, as I said, I mean, we are not only interested in short-term behavior, but we are also looking for long-term behavior. So here we also look at the attractor, the construction of the attractor and projection. So here, like on X, on the projection of the attractor on the X-axis before, after training, before training, on the x-axis, xy. On yz is these two figures, and sorry, is it like, yeah, no, sorry, it's like xy, xz, and then yz axis, and yeah, and that's the 3D attractor. So on the left side is the reconstruction and after learning, and the right side is before learning. So we see an improvement in the performance. So then, yeah, once we uploaded this work on the archive, someone from Argonne National Lab approached us with data that's like real data from climate modeling, and yeah, so in this national lab, they use two PDE methods. So one of them is called HiCom, and the other one is CSM. So for the data set that they provided to us, we have. So they use I mean, it takes them like 800 core hours per day of forecast on a Cray XC40 system. On the CSM, 17 million core hours on this supercomputer. On LSTM, using LSTM, it's like 3 hours of hold time on this Theta supercomputer. And then using my our method, I'm using my laptop. I mean, it took like 40 seconds of training. And you see that this works quite well here. So the data, the red data is from the satellite. Blue is kernel flows. Orange is PDE, and then green is CSM. And you see, I mean, it's doing quite well. So the method works quite well. That's the temperature profiles. I mean, here you see the true kernel flows and HiCom and CSM. And so here apparently it's you see, I mean, but it's doing quite well. And apparently it's doing well as well, and because it's detecting some Enzo cycle as well. Yeah, another version is the non-parametric kernel flows. So where instead of learning the parameters of the kernel, so like, we have like parametric kernel flows where we are learning the parameters of the kernel. For example, we start with this kernel, for example. And then we want to learn these parameters like alpha 0, sigma 0, alpha 1, sigma 1, alpha 2, sigma 2, until alpha 4. Non-parametric kernel flows starts with different premise, is that we want to deform the data. So one is like learning the parameters, and the other one is deforming the data in such a way that we learn the kernel. So here we want to, so we start with the kernel K, and we deform KXX prime, and then we deform the data using a flow. So we want to deform the data using a dynamical system itself to define a new kernel. So the warping of the input space satisfies the following ODE. So this is like the dynamics of the warping. And this after discretization. So the discretization gives us the following Euler scheme. And yeah, so this is what we see here, for example, like for in the case of the Bernoulli map, this is what we have. And so on the left side is that we are using the classical row. The right side, we use the row MMD that we talked about earlier. So you see that, yeah, so it's still like a good prediction. So prediction is blue and true is red. And this is the deformation. For example, we start like Pn is equal to Xn, so that's the blue, and then with green is what happens after 50,000 iterations. Yeah. So this is the data. I mean, the true original data set is green. Sorry, original training is blue, and then original testing is green, and then warped. So this is what happens to the warping train, and warping testing. And this is the error. I mean the convergence, the loss function for the classical error versus the MN. Yeah, this around, yeah, so that's one another thing. I mean, around the same time, I mean, someone else from healthcare, I mean, he wanted also to check our method on data with coming from healthcare, but he said that in healthcare, I mean, data are not coming not all the data are coming at the same time, and you have like some data coming at a certain period, another data coming at another period, etc., etc. The way we solve this problem is that we introduce the time differences, delta k equal to tk plus 1 minus tk in the data set. So we would work with the following extended state. So xk, so instead of doing like xk minus 1, xk minus 2, we do xk delta k, xk minus 1, delta k minus 1, etc., etc. And then so working in this extended state, where we can map, we can solve our problem, and this is what we see here. For example, this, if we have like irregular sampling of the Lorentz, you see the method does not work, and also we do not reconstruct the attractor. But by working on by using our trick, I mean the method works well. So this is, for example, for the case of Lorentz. So left side is regular Kernel flows, right side is the irregular Kernel flows. You see there is a good improvement, but also same for the attractor. So the left side, you see it's not looking like the butterfly that we are familiar with, but the right side, I mean, looks much better. Another extension is the case of partially observed dynamical systems, where we have we assume that we have xk plus 1 is equal to fxk is equal to fnx and fmx. We assume that xn is observed, and then xm is not observed. So we only observe the first n states, and then we do not observe the other ones. So here we reformulate our problem, and we add this constraint here. So I mean, here is overflowing, but yeah, that's yeah. So we reformat our problem as follows, and then this is the following optimization problem that we could solve using gradient descent. And so here the kernel gets bigger because so the smaller kernel is not that expressive, so we need to have extra kernel, extra elements. And so that's so this and also the other thing that we notice that one needs to increase the time delay from 3 to 4, and you see there is so it works quite well. So this is what happens with learning partially observed dynamical systems in the case of Lorentz. So these are the errors, and this is the attractor. So the blue is true, and the red is the approximation. So now we want to look at the other, So here, so we started with kernels. I mean, the way we were doing it is mostly do them by hand. So here we want to look at the other side, like doing it in more of instead of doing it in inductive ways. So here we want to do it in a deductive way. So we start with a large dictionary, and then we want to sparsify the kernel. So this is what we call sparse kernel flows. And our goal here is to look at, so we are interested in the following cost, but we add a penalty term, and then we want to, so this is beta, there's a typo here. So we want to fix, to make sure, to make some of the coefficients to be 0. For example, we will start with this large kernel that has 40 parameters. And we want to make some of the coefficients, some of the thetas to be 0. And this is what we see here. For example, like we apply this actually to one database of 131 chaotic time series, and the method works quite well. So this is like an example of this chaotic system. So you see, this is like classical kernel flows. This is the true versus approximation of the attractor. And then the other one, the right side, is what happens with the sparse kernel flows. So you see there is an improvement. Same thing for this example here, the true electronic system. So we have the regular kernel flows without specification, and so this is the attractor, and then this is what happens when we do specification. So lambda is equal to 2. And so this is like, for example, the error. So we see like the are with regular Kernel flows versus after with sparse Kernel flows. And this is Hausdorff, the Hausdorff distance between the true approximation, between the approximation and the true attractor is 278 versus sparse, and same thing for the other example with Yeshua, and then we see that it's decreasing. Detection. So how much time do I have left?
About a time. Okay. Okay. I can give maybe 10 minutes for you.
10 minutes. Okay.
Yeah.
Sounds good. Yeah. Okay. Yes. Another point is the detection of critical transitions for multi-scale systems. So here we adopted two approaches. So we are looking at this slow-fast dynamical system, like this slow-fast SDEs. So they have slow component versus a fast component, and we'll illustrate it on the van der Pol model. So these are the X1 and X2, and so the way, the first approach we adopted is to look at the MMD. So we look at so we prove that the maximum discrepancy that we talked about before earlier gets maximal at the critical transition, and this is what we see here, for example, in the case of one of the variables, that the MMD gets maximal here. So same thing for these variables here. And yes, that's one thing. Then the second approach we adopted is to do like micro-local kernel design, where we start with a Gabor wavelet and then use modify it. So instead of looking at these patterns, cos omega t minus tau plus theta, so we use the following pattern, which is like y is the pattern that we are interested in, and then from there we construct the following kernel. So k s theta is equal to xc s xt, with xc being the following function. So that's the micro-local kernel, and then we integrate with respect to all the variables to get a larger kernel. And then, for example, in the case of stochastic van der Pol, so we are interested in detecting this pattern, and then by using this trick that I just talked about, we can construct a kernel that is detecting the critical transition as we see here. So that's what we see, for example, here. And then we also do a sort of separation between noise and signal, because in the case of SDEs, we have like intrinsic noise. So we do separate between signal and noise. Then we also want to detect critical transitions. The way we are going to detect it is that we are going to define the energy of sliding window. So we have a sliding window that is moving, and then we compute its energy, and then we want to show that it's maximal around the critical transition. And this is what we see here. This is what happens is that we see that if we have this signal here, so the blue is the blue is the signal, and the red is the energy of the sliding window. And what we notice is that by playing on the parameters of the sliding window, we see that there is improvement here in this energy, and then we could eventually use it for prediction. So it's not only for detection, but also for prediction. But there is this parameter tau, that shows up in the Gaussian, that if we make it too large, then we are going to miss the critical transition, as we are seeing here in the third figure. So we see that there is a possibility of extracting an early warning signal for this kind of systems for properly choosing a certain parameter. So maybe I'll just stop looking at next. So another thing is that, remember, we are talking about like prediction and short-term behavior, but also we can look at long-term behavior, and for example, have a database version of the center manifold theorem that we are seeing here. Assume that we have an equilibrium point. We have a dynamical system, x dot is equal to f of x, and our goal is to analyze the stability of this equilibrium point. So if all the eigenvalues of capital F has negative real past the origin is asymptotically stable, if some of them have positive real part of the origin is unstable, and this is something that we know. But as we know also that if some of them are on the imaginary axis and other ones that have like negative real part, then the linearization test fails. And this is where the center manifold theorem comes into play. So the intuitive way of explaining it is that we are going to decompose the variables into two parts, x1 and x2. x1 corresponds to eigenvalues on the imaginary axis. x2 corresponds to eigenvalues with negative real part. So intuitively, we expect the stability of the equilibrium to depend only on the x1 coordinates, because the x2 coordinates will eventually converge to 0, to the origin. And that's exactly what the center manifold theorem is about. It's telling us that there exists an invariant manifold x2 is equal to theta x1, tangent to x1 direction at x equal to 0. And then this theta satisfies the following PDE. And we want to, so yeah, our goal here will be, we assume that what we did, we are going to assume that we have only data, and we want to solve this PDE using kernel methods. So the center manifold theorem is telling us that the equilibria of the full order system have the same stability properties of the reduced order system. So after solving this PDE, the problem of studying the stability property of the full order system reduced to the ones of the lower order system. So as I mentioned, our contributions said that kernel methods we are going to use them to approximate the center manifold. So we are going to use kernel method to solve this PDE to find approximation of theta. And from there, we are going to have a weak database version of the center manifold theorem. So this is what, given the constraint on theta, we are going to use like a generalized representative theorem. So we are going to take into account we are going to add this extra term. And then under certain conditions, we prove that if the equilibrium point of the lower order system is asymptotically stable, then the equilibrium of the full order system is also asymptotically stable. So in a way, we are dealing with asymptotic stability preserving property in one direction at least, and the second direction is still missing. We also prove that x1 theta minus x1 theta hat is bounded. So we consider that's like an example. So we have like this two-dimensional system. One can find the center manifold analytically by solving the PDE using Taylor series expansion. So what we did here is that we used two kernels. One is the quartic and the other one is the Gaussian kernels. So here, these are the errors between these are the true center manifold and the approximation. This is y is equal to minus x squared. This is for k1, this is for k2. And yeah, for this system here, the center manifold is dimension 2. So we also use the same kernels for that quartic, sorry, and Gaussian. And then these are x1 and x2 components here. So which means that it's working well. Yeah, so you told me, so is it over now or is it? What time?
Hamzi, how many time you need? Okay.
Well, I have a lot of slides. Yeah, so I can stop here. Yeah, I think I can stop here, or I can add 5 minutes for Lyapunov functions. So do you want to see Lyapunov functions, or you want me to stop here?
Okay.
Yeah, so yeah, I'm going to go quickly over Lyapunov functions. So another thing is construction of Lyapunov functions from data. So here we have nonlinear ODE, x dot to f of x. So we approximate f from data, and then we find the Lyapunov function for the approximation. And then we prove that v hat is also a Lyapunov function for f. So yeah, I'm guessing that yeah, most of you know what Lyapunov function is and how. So basically, it's just a function that is decreasing along the solutions. Then here we have existence and a way of constructing Lyapunov function by looking at this PDE here. So instead of looking at differential inequality, we are going to look at this PDE. And yeah, so yeah, under certain conditions, we proved that yeah, that we can do that. I mean, that, for example, that's the example here. So we start with this example. We generate data, and we know that the true Lyapunov function is x1 squared plus x2 squared. So what we do is that we also solve a PDE for the Lyapunov function that is given by the following PDEs, that the orbital derivative LV1 is equal to minus P with P some positive function. So here we're going to use the norm of x squared. And and then it works well. I mean, the method works quite well. So that's an example of the Lyapunov function when we increase the number of points. And that's the orbital derivative where we are decreasing. We see that it's decreasing. It's negative, and then it's decreasing. Yeah. Okay. So I'm just going to conclude. Yeah. So here what we did is that we used the method of kernel flaws to approximate chaotic dynamical systems. We used the maximum mean discrepancy and extended kernel mode decomposition to detect critical transitions. So I didn't talk about this, but I also talked about database approach to construct Lyapunov functions, and also approximate center manifolds. And then also we have weak database version of the center manifold theorem. And all these results, and we collectively argue that working in reproducing Kernel Hilbert spaces offered tools for database theory of dynamical systems. And then these are the slides. So all the papers are on arXiv and ResearchGate. Yeah. Yeah, thank you for your attention, and then please feel free to ask me questions. Yeah, thank you.
Okay, thanks for your nice talk. Now about time of discussion and advance maybe questions. Okay, please now my question participations. Please, if you have question or maybe advance and discuss, please. But Hamzi, you understand here many mathematicians in our seminar, so such type rich materials